I will try to, well, I will be a bit more mathematical. The goal of this talk is to try to give you what's the underlying theory behind doing statistics on curved manifolds. So first, the general goal, so if you have seen already, in computational anatomy, what we're trying to do is to, well, not only design statistical methods, but also the algorithms to model the anatomy. And basically, the first ideas that we want to do is to compute the mean shape, to compute the shape variability, so something like the covariance matrix, and then maybe to try to see how that evolves over time. So there's a high interest for that, and that will be part of this talk, how the shape is evolving over time and how we can correlate that with clinical variables. So the first example of shapes is the Kendall shape space that was already presented. So now you should know, or at least have the idea that so when you're taking a set of points, if you're removing whatever is related to the orientation, the position, and maybe the scaling or the full affine transformation, so basically you're removing what is due to the action of a group, then we have equivalence classes, and then the set of shapes is a nonlinear space. So the whole point that I will try to address here is not about the Kendall shape space or another shape space, but to try to see what are the structures, the mathematical structures that we can use to actually compute in these nonlinear spaces. The second example, and I will illustrate that a bit more in my talk, is morphometry using deformations. And the basic idea is to say, okay, we're going to have a mean shape that we call often the atlas or the template, and we're going to encode the other shapes by the deformation of these mean shapes towards each of the shapes that we have in our population. So now the idea is, this is the mean, so the mean is a shape itself, but the variability will be encoded by deformations. And what we need here is to be able to do, well, to compute the mean, so that's the atlas estimation. So there's lots of work in the medical image analysis community on how to compute an atlas. But the second step is how to compute statistics on deformations. And that is, so what's the covariance matrix, for instance, of a deformation? What is a mean deformation? And that is exactly the subject of this talk, how to do that, so how to do statistics on groups of transformations. And groups of transformation, we call them usually Lie groups. And the key thing will be to do that in a consistent way so that we can compose transformation, and statistics that we're doing are consistent with that. So the last problem that I will address in the talk is longitudinal analysis. So if we see patient 1, the image, so we can take the shape of his brain and see how this is evolving over time. So we could, for instance, encode the deformation over time using, well, we can find it using registration, and then we have a deformation trajectory over time. Now we have a second subject here, and if we want to do group statistics, what we need is to transport these patient deformation trajectories in the template so that we can somehow compute the average deformation for the population. Now there's one problem here, which is that if we want to resample an image, we just take the value at the corresponding point by the transformation. Okay, so it's a simple resampling. Now, if we want to transport a vector field, if the transformation is rotating locally, we would like to rotate the vector field with it. So there's more than just resampling. We need to transport. And here there is a choice. How do we transport? And we need to have numerical techniques to do that behind. Okay, so the questions that will be here is how to transport longitudinal deformation trajectories, and once again, is there a convenient mathematical setting to do that? Okay, so the talk will be organized in three main parts. So the first part is trying to explain what's the Riemannian framework to work on these nonlinear spaces. And I will try to start from scratch so that you can at least have an idea of what's happening. And you can always come back later to formulas or, I mean, the idea is just to get the big picture. So don't get lost if there's something you don't understand right at some point. You'll get it later, okay? So you can come back to the papers. The idea is really going to the big picture. So I will first do the Riemannian framework. And then in the second part, I will try to explain you why I'm not satisfied with that. And I need to be, maybe to go a bit further away. There's some echo, I think, no? No, it's okay with the microphone? Okay. And then we will see applications for the longitudinal setting with the stationary velocity field framework, so basically the log demons that I presented yesterday. Okay, so first, nonlinear spaces, manifolds. What are these? Well, it's basically the definition, the mathematical definition is it's locally a Euclidean space. So it's locally flat with a metric, with a Euclidean metric. The only thing is that globally it's curved. So the simplest example we have is the sphere. So this is why you often see all our representation with a sphere, because it's a good visualization of a manifold. But we could have as well the saddle here, so it's a hyperbolic space. Or, of course, if we have a plane, this is also a manifold, but that's a simple one. That's the one we are always using, okay? So these are typical manifolds, and this will be the manifold that I will use as example because we can clearly see what's happening. So other types of manifolds are projective spaces. If you see if you project all the points along a ray, and we could see, for instance, rotation in 3D as a projective space. So this is a good picture to have in mind rotations, although this would be a projective, well, something like a sphere, but in 4-dimensional space. Okay, now if we want to compute on a manifold, usually what's done, well, there's two ways of seeing things. One is to see, if you see the Earth here, you can see it as an embedding in a larger space. So you can see this is a 2-dimensional manifold. The surface has 2 dimensions, and it's embedded in a 3-dimensional space. And there is some kind of metric measurements. If we want to measure distances, we can measure distances in the ambient space and try to see how does that propagate to the manifold itself. But if we're going to very large dimension for manifolds, then we need to have even larger embeddings. So if we go for diffeomorphism, for instance, it might not be possible to actually put in the computer a space which is large enough to do the embedding. So the other way of doing things is to take charts. And if you think of the Earth, it's just geography. I mean, if you want to drive, you don't need to have a 3D model of the Earth. You just need to have locally something where you flatten the Earth. But if you want to represent the whole manifold, then you need to glue together several charts. And if you want to represent the whole Earth, you need actually what is called an atlas. So that is exactly the mathematical definition that we're using. A complete set of charts which are consistent with each other is called an atlas. Now in this talk I will assume that everything is completely smooth. Okay? There are manifolds. We can talk about manifolds which are smooth up to a certain degree or just continuous. I will just assume that everything is smooth just to simplify, okay? Just to get the picture. Okay, now the big question that we want is how do we make measures on our manifolds? And the measure we would like to do are volumes. So in the case of the Earth, that would be surfaces. We could measure lengths, and we would like to have straight lines, something like straight lines, okay? So the main question is how to do that in a way that it is consistent with the embedding and within the charts, if we take the two approaches. And the main problem is that if I'm taking now this manifold, which is a simple one, it's a surface, a 2-dimensional manifold, and I drew on it areas which are more or less the same on the embedding. Okay, now I take a map, a projection to take a chart, and this is one chart that is parameterizing my manifold. And you see that the unit volumes are distorted. So basically, if I'm measuring volume in this chart with a Euclidean coordinate system, that will not be consistent with the embedding. Likewise, if I'm measuring length, the length of this curve here, it will not correspond to the length in the 3D embedding. So how to deal with that? How to design a way to do consistent measures which do not vary with the chart that you're taking? Well, the idea is to go back to the basics, and the basics is the scalar product. So in a Euclidean space, so we can think here of the embedding space. If we have two vectors, with the scalar product, we can compute the norm of a vector. We can compute the angle between two vectors by taking this type of formula. I don't really care the formula. The idea is just that with the scalar product, we can do that. Okay? And now if I have a curve, I can compute the length of this curve by taking the norm of the tangent vector along the curve and integrating it. Okay? Now how to use that in a manifold? Well, the basic problem is that if I'm taking a coordinate system here or here in the ambient space, they do not project in my chart as orthogonal anymore, right? And that is exactly where the problem comes from. And the idea of Riemann was just to say, if I want to have intrinsic measurements, I just need to set up, well, to specify what is the scalar product at any point. And now, instead of having just on one point, I will have given the scalar product at that point, and now I can project what is the scalar product here and see how does it project in this chart. And when I will change my chart, the metric in the chart will change accordingly. And so if I have this scalar product at any point, I can now compute the norm of a vector at a given point. Given the scalar product at this point, I can compute the angle between tangent vector at one point, and I can compute the length of a curve by integrating. The only thing here is the metric is depending on the points where we are on the manifold. Right. So now when we have the length of a curve, we can ask another problem. What's the shortest path, or what's the straight line between 2 points? So if I'm saying, well, the definition of the geodesic is usually to take the shortest path. So basically, the idea is to try, if I'm starting here and I want to go here, along all the curves, I will try to select the one that has the minimal length. Okay? So usually what we do, well, to do that is to compute an energy rather than the length. And we can show that there is, well, we can take the derivative of that energy, and this is giving us what we call the Euler-Lagrange equations, which are characterizing the geodesics. Okay, so no equation is just the idea that we can do it. And mathematically, there's one thing that is important here, is that the Euler-Lagrange equations, they are a set of second-order differential equations. And you know that when you have a differential equation, a first order, when you integrate, you have one parameter which is free, which is the starting point. So if we have a second-order differential equation, we will have the starting point as a free parameter and the starting velocity as another free parameter. So this is very important because it means that we can parameterize the geodesics by the initial starting point and the initial speed. And that is the basis of computing in manifold. The idea is that if I have a point and a tangent vector, this is characterizing a geodesic, and I can derive a mapping which is where do I end up in the manifold if I shoot starting from along the geodesic, starting from this point with this tangent vector. And this is what we call the exponential map. So the exponential map is taking a tangent vector at one point and giving a point in the manifold. Now locally, we can show that this is a diffeomorphism, so we can take the inverse. And the inverse will be called the log. Well, that's x log. So the reason why it's called x-man log is that in some cases with bi-invariant metrics, this corresponds to the matrix exponential and log on matrix Lie groups. So that's the reason why it is called x-man log. And we will come to this matrix Lie group a bit later. So here the idea is with this x-man log map, we can compute, if we are able to implement that, this is the basic bricks to build anything in the manifold. So the mathematical setting is done. The only idea is, instead of, when we are thinking about vectors in a manifold, we should think that they have a foot. Okay, the vector xy here is starting at point x. And you can see that if I'm taking a tangent vector at point y, it will be in a different tangent space. Okay, so we cannot easily compare a tangent vector from one tangent space or from one point to another. But if we come back to the original definition of vectors, they are defined usually using the equivalence classes of bipoints. And here we should think a vector is a bipoint. That's basically a vector with a foot. Okay? So this is the thing that we have to remind. And now we can try to rephrase some of the usual Euclidean space operation. So what's the difference between 2 points? It's a vector, and it's the vector that is allowing to shoot from one point to the other. So it's basically here the vector, which it would be the log. It's the vector that is allowing me to shoot from x to y. And you see that if I'm taking y minus x or x minus y, it's not the same. Here, the vector that is shooting from y to x would be in that direction. Okay, so there is, in between the two, there is a relationship, but it's involving a higher order operator that we call parallel transport. Okay, now what does it mean to add a vector to a point? So adding 2 vectors makes sense if they belong to the same vector space, but adding 2 points, does it mean something? But can you think of adding the position, 2 positions in the Earth? Doesn't make sense. What we can add is a vector to a point. Okay? And that is exactly, well, we're adding a vector to a point means that we're starting with a point and we're shooting along the geodesic which has this tangent vector. So that is the exponential. Okay? The distance between 2 points is the norm of the difference, usually in a Euclidean space. Well, if we just use the rules that we have, we take the vector that shoots from x to y, and we take the norm of that. The only thing is the norm should be taken at point x, because remember that our metric is depending on the point. Then this is the distance between the 2 points. So it seems that we have almost everything to work with. Okay, we can do gradient descent as well. Okay, so that will be the basis for implementing things in manifolds. Now, if we want to do statistics, we need a little bit of probabilities. We need to know a little bit what is a random element in the random variable with value in the manifold. So we usually specify that by the probability density function, which is the probability to belong to a set. So now the big question is, what is the measure? Here we usually use the Lebesgue measure, so just dx, dy, dz in 3D. So the main problem is that if we are taking one chart or the ambient space, you see that the measure is changing. So one thing we need to do is to correct for the change of the measure. It's basically the volume which is here. This is the reference measure of our space. And if we have a Riemannian metric, then we automatically have a reference measure. It's basically if you take at a point the tangent vectors and you take an orthonormal basis, and this is spanning well, in 3D a tetrahedron which has unit volume. That's your reference volume. So we have that. From the Riemannian metric, we have a uniform measure on the manifold, so we can define intrinsically probability density functions. Okay? We just have to remember that we are not using Lebesgue's measure, but the Riemannian measure. Okay, that's something we can do. Now, a second thing is we want to have mean values, and this is usually done using expectation. So the expectation of a function from the manifold into a vector space is simply the integral of the value of that function over the whole PDF. Okay? That's a standard formula. And usually what we put is we are putting an x here to say what this is the expected value. So we can't do that anymore. What we can do is we can take the expectation of the square distance to a given point, and that will be basically the variance with respect to that point of the distribution. We can put log of p. P is an intrinsic density, and that will be the information. But we can't put an x or y here. We can't integrate with the value x and y, because this would be an integral with value in a manifold. And an integral is a linear operator, so mathematically there's no way we can have a linear operator with value in a nonlinear manifold. So there's no way we can have an expected value as usual. So the trick, and that's what Guido presented previously, the trick is going to Fréchet mean. And in mathematics, when there's something which is not scaling up, usually what you do is you change the definition. You take a consequence of the previous definition as the new definition. And for the mean, what we know is in the Euclidean space, the mean is minimizing the variance. And the idea of Fréchet was to say, okay, I know how to write the variance in a metric space, so I'm going to use the minimal variance as the definition of the mean. That's very simple. Okay, that's our new definition. We're going to take the set of points that minimize the expected square distance. That's our definition. And we can show that if we are in good conditions, when we are at the mean value, if we develop everything in the tangent space, then the integral in the tangent space is 0. Meaning that when we are at the mean point, if we develop everything, so that's called the tangent development, if we take the log of all the data points, the mean value is 0, corresponding exactly to the mean point. The geodesics toward the data points are now straight lines. Seems that we can do many, many things, and in particular what we can do is we can do covariance matrix and things like that. So there's just one thing which is a bit annoying. Well, I said we're going to define the mean as the set of points that minimize the variance. So, well, we don't have always one unique mean. Is that a problem? Well, usually we used to say we have the mean, and there's only one. But if you just imagine a bimodal distribution, does the mean really mean something? We would rather take the modes, okay? And are the modes unique? Well, no. If you have a bimodal distribution, you will have two modes. So is it really a problem? No, it's a modeling problem. We should just know what we're dealing with. So if the distribution is sufficiently concentrated, then there is a unique mean. But if we have bimodal distribution, and if you just take a sphere with high probability on both the north pole and south pole, you will have a bimodal distribution. And there's no way you can have a unique mean here. So this is something that we lose, but we are not losing too much, because actually we're always thinking that we have a unimodal distribution. So in this case, everything's working. And even more, in practice, when we compute the mean, there is always almost surely a unique mean. So actually we can do as if it was not a problem. Okay, so once we have obtained the mean, and the algorithm was nicely illustrated by Guido, so I don't need to come back to that. It's a gradient descent on the variance. Then we have the mean, and when we develop everything, we have a tangent space representation, which is a linear representation of the data. So it's linear with respect to the development point. So along the geodesics, starting from this point, it's linear. Now, if you take 2 points, it will not be linear between 2 points which are anywhere. But with respect to the mean, it is linear. And in this space, we can define the covariance matrix. So the covariance matrix will be sitting in the tangent space at the mean point. We can define the covariance matrix at any other point, but it will have a minimal norm at the mean. So that's the idea which is behind the analysis, the tangent PCA analysis. So either we can see us projecting on the manifold. Here the idea is the log is developing, but it's not very far away. I mean, it's the same type of idea, projecting on the tangent space or developing in the tangent space, and then analyzing in the tangent space. The other thing that can be done is to try to see what is the subspace. I mean, when we want to decrease the dimensionality, so we can select what are the best eigenmodes of the tangent of the covariance matrix, that tangent PCA. We can also try to see what's the subspace which is generated by the geodesic starting at the mean point with a given number of vectors, and that's tangent, PGA, principal geodesic analysis. So these two, they do correspond in a Euclidean space. They do not anymore correspond in a manifold because the Pythagorean theorem does not hold, basically. So minimizing maximizing the explained variance or minimizing the residual with a model is not the same in a manifold. Okay, it's just to say that. Now, if we want to do some statistics and some parametric tests, we need to have distributions, and the simplest distribution is the Gaussian. So how would you define the Gaussian in a Euclidean space? Well, there's many, many ways, okay? None of them is coming to you. Well, from an engineering point of view, what I want to do is I have a distribution, but the PDF is much more complex, too complex to put in the computer. So what I want is to simplify it, and usually we take the moments. So we take the mean and the covariance matrix. Now, can we characterize the Gaussian distribution with that? Well, among all the distributions that have the same mean and the same covariance matrix, the Gaussian distribution is the one that maximizes the entropy. In other words, that's the distribution that do the least assumption when we just know the mean and the covariance matrix. So this is quite a nice definition from the engineering point of view, because, I mean, if I'm just computing the mean, the covariance matrix, I want to assume the distribution that does not add information. And if we take that as a definition, so once again, changing the definition to a property, so here we can define this optimization problem on a manifold, and we find this kind of distribution which looks like a Gaussian. Okay? It's written in slightly different notations. We have here, these are vectors to the tangent space at the mean point, and this concentration matrix here is not exactly the inverse of the covariance matrix. It is related, but there is a term here which is the curvature of the manifold, which is entering into the game. And basically, the idea is that if the curvature or if the dispersion of the data is small with respect to the curvature, then we can forget this term, because sigma minus 1 will be larger than this. And that's the only thing we should retain of all that. If the data are more concentrated than the radius of curvature, we do not care much once you have center at the mean. I mean, the distortion that we have is not much. Now, as soon as we're going to be larger, the distribution will be larger than the curvature, then we should probably take care. Okay? So the message is quite simple. It's actually, if you just look at a few things, then you can avoid all the problems and all the difficulties that I'm just trying to explain you. But you should be aware of that. Okay, so once we have the Gaussian distribution, we can look at other things like Malanobis d-square distance, and we have some types of properties. So basically, if we have a Gaussian distribution, we can show that it's basically a chi-square distribution if we are sufficiently concentrated. So this means that we can do also test statistics on manifolds in a proper way. Okay, now what I'm interested in this talk is manifolds whose elements are transformations. So these manifolds, they are also what we call a Lie group. If we assume that there is transformation, so we can basically compose like rigid body transformations or rotations. We can compose them. They are still belonging to the same set, okay? Now, if we put a metric structure, a Riemannian metric on this, which is compatible, so in a mathematical sense, so basically which is smooth, then we have a Lie group. So that's basically the setting for the transformation groups. That will be a transformation group with a manifold structure, okay? So all the transformation groups that we can deal with are Lie groups, even the infinite dimensional ones. The ones we work with, they are Lie groups. They are more complex things, but we don't want to see them. Now, in a group, I have the composition law, okay? And I have also the inverse law. And now, if I have a set of transformations, I could think of composing all of them on the left by left composition or on the right by a fixed element, okay? So this is typical in a Lie group. We have the left and right composition, and because it is not commutating, and if you just think about matrices, they do not commute when you multiply them. So multiplying on the left or on the right by a given matrix is not giving the same result, okay? So in a Lie group, if we want to put a Riemannian metric, the idea is we have the tangent plane at the identity, and to go to any element, to any transformation, we can compose on the left or on the right by this transformation. So if we have a metric in the tangent space at the identity, we can propagate it to any point of our group by left or right transformation. This is called left and right translation, even if it's rotation. And this means that all the metrics are very easily parameterized by the metric at the identity. And we have, from the computational point of view, we have a very simple implementation. So I don't want to enter into details, but it's basically, once we have the exponential map at the identity, the exponential and log map, we have them anywhere if we have a left or a right invariant metric. So that is a way to work easily in groups. And here is an example of a statistical analysis. We have here a spine, and we want to study the shape of this spine. So what was done is actually X-ray from frontal and lateral X-ray, and then on these specific points were pointed out in the two views and reconstructed in 3D. And these points, this is what we used at the beginning. So of course what they tried to do is PCA. And the result was, well, they need probably something like 30 or 40 modes to represent 80% of the variability, and the modes doesn't resemble anything. And when you think of the shape of the spine for scoliotic subject, it's quite varying. And it's varying too much to be captured by just points. So what we thought is, what's the feature in this shape? It's basically an articulated model. So what's important is more to encode what is the relationship between the neighboring vertebra. So if we encode the shape by the translation and rotation between the neighboring vertebra from one vertebra to the next, then we can encode the shape by a kind of vector of 17 rigid body transformations. Okay? And that's our shape vector. And now we want to do statistics on that. Well, fortunately, we have the artillery, now all the tools to compute mean values, covariance matrices. So we don't need to bother that we are on a nonlinear space. We can do the statistics. And if we do that, we end up with these modes. And so this is lateral and frontal view. And these are the four first modes. And what you can see is, well, the first mode is basically related to growth. And what's interesting is that related to the growth, there is an increase of the scoliosis here. And it's known, 1 degree per year. We find it in the data. Now, the second and third mode, these are just the free oscillation of a rope with one node in the middle here and no node. So it's basically an oscillation mode with these 2 points which are fixed, and here we have 3 fixed points. And the third one is basically just the lordosis, so the angle here. And you see that everything is correlated because if you're augmenting the angle, here everything, well, the head is staying more or less horizontal. And that's well known. I mean, you're trying to stay, even if you're curved, you're trying to stay with your vision, which is horizontal. So the nice thing is with 4 modes here, by a correct geometric modeling of the shape, we are actually inputting some prior knowledge on what we want to analyze. And it is geometric. It is on a nonlinear manifold, but it is simplifying a lot the analysis because now we can see exactly what's in the data. We are not messed up with the dimensionality of all these points and the correlation that they have. So we can use the real nature or the interesting nature that we're interested to analyze. A second example is the shape of the heart. So just imagine that, okay, so for that I need to introduce the shape space of diffeomorphisms. So instead of going, in the previous example I was on rigid body transformations. So that's 6 degrees of freedom. So it's matrix, it can be represented with matrices, so it's simple to implement. Now if we go to space of general deformations, what would be the manifold? We want to have invertible manifolds, invertible deformations, because that is a requirement for a Lie group. But basically we take the space of transformations, and a curve in the space of transformation would just be a transformation that depends also on the point, but on the time. Okay, the time here is just the arc length parameter of your curve, if you want. Okay? Now, what is a tangent vector? That is the derivative at a point of a curve. So it's basically the derivative of a time-varying mapping, so it's a speed. Okay? So a tangent vector to a diffeomorphism is just a velocity vector field. That's as simple as that. Now, what is a Riemannian metric? It is a metric on vector fields that depend on the transformation. And if we take a right invariant metric, it means that we take our velocity field, we pull it back to the identity by the inverse transformation, and then we're taking the norm. And the norm we are taking at identity is usually either a Sobolev norm or a reproducible kernel Hilbert space metric, and that is leading to diffeomorphism. So diffeomorphism is very simple. It's just a series or the flow. Now, what is what is generated by these curves? It's a flow of time-varying velocity fields. Okay? So that's quite simple. Now, the geodesics, they want to minimize the distance or the square distance. So basically, the geodesics will minimize the length of the curve between any 2 fixed deformations. And as we saw previously, any geodesic is characterized by the initial starting point and the initial velocity. So we can characterize, in LDDMM, we can characterize a geodesic by the starting point and the initial velocity field. So we used to rather use the momentum, which is the, you can see it as the quantity of motion. So it's basically you take an object, you start at one point and you throw it with some kind of quantity of motion, the momentum, and then the free fall will be going along the geodesic. So that is more or less what it is. Okay, so if we use that, that step, then we can encode the deformation of shapes, and here we're interested in the shapes of the right ventricle in tetralogy of Fallot of the heart. And the idea is, here you see, normally the left ventricle is much larger than the right one. Here in tetralogy of Fallot, it's a combination of disease where, I mean, it has to be corrected by surgery very, very early, but there is some regurgitation from the pulmonary artery, so the right ventricle has an enormous work to do to push the blood into the lungs. And this is involving an increase of its size. And now the key question is to understand when do we need to put a valve, a new valve, the latest as possible before, because the valve has a finite time or duration, but we should do it before the heart is completely damaged. So one of the ideas was to try to analyze the shape over time. And to do that, we take 18 patients, 18 subjects, and these are the shapes of the 18 patients. And you can see that they're varying quite a lot. And what we want is to compute the mean value and to compute the correlation with respect to the age. Okay, we want to regress the shape over age. So what we can do is compute the atlas, so that would be the mean shape. So this is not the shape of any right ventricle of the population, it's the one which is computed with the Fréchet mean. And then we find what are the modes of variation. So these are the first mode of variations, the deformation modes. So you can see that they're describing quite a lot of things, but even the first one is basically shape, but there's not only shape, well, size, I mean. There's usually when you're doing PCA, you cannot really analyze each mode independently. They are interrelated. Now, if we try to relate that to one clinical variable, which is what we're interested in age, and we're actually using a surrogate variable, which is body surface area, to take into account, well, small and large childs, we can see that only 6 modes are correlated. But if we're trying to make the regression now, so we have a population, a single population of 18 subjects at different age, and we're just trying to infer what is the shape change over age that best explains the data. And this is what we find. And interestingly, if we go through all the details that we can see, we can retrieve a clinical explanation of that. All of these parts were described in the literature, and we can see all that in the model that we found. So that seems to be a good way to do the analysis. Okay, so now in the last minutes, so that will be very short. I'll probably skip a few slides. Why am I not happy with this left or right invariant metric on Lie groups? Well, the basic problem is that if I'm doing statistics in the Lie group, I would like my mean to be invariant by the left translation, invariant by the right translation, invariant by inversion. These are the natural operations on the group. So if I'm lifting all my measures on the group, I want to have a notion of a mean which is invariant with the group operation. And actually, this can be done with left or right invariant metric only if the metric is left and right invariant. And this can only happen if the group is very simple, actually if it's compact or if it's abelian, commutative. So it means that for rigid body transformation, there's no such a thing, there's no bi-invariant metric. So it means that if I'm taking a set of transformation, rigid body transformations, and we can even take that in 2D, I'm taking a set of transformations, 3 of them, I'm computing the mean. Now I'm taking their inverse and computing the mean. And the mean of the transformation, or the inverse of the mean, is not the mean of the inverse. So it means that now, if I use this type of statistical structure, I'm completely dependent on the order on which I will compute things, which is not satisfactory from a mathematical point of view. So is there a way to get a more convenient structure? The answer is yes, but we should give up the metric. And that's so I'm going to skip the Lie group stuff, but the idea is I define everything in the Riemannian setting with geodesics. And I define geodesics as shortest path between 2 points. Now, the second definition we can use is straight line. A geodesic has no acceleration, okay? And to compute the acceleration, what you see here is that the tangent vector here is not exactly lying in the vector space of a neighboring point. So if we want to compute the acceleration, we need to compute the difference between this vector and this vector, but they do not belong to the same tangent space. So what we need is a structure that allows us to project one tangent space to the neighboring one. And that is called a connection, or an infinitesimal parallel transport. So if we're given that, then we can compute an acceleration, and we can require that the acceleration of a curve is 0. And once again, we have a second-order differential equation, and we can define the geodesics, and we can define exponential and log map exactly as in the Riemannian case. The only difference is that in the Riemannian case, we have a global existence of exponential, and the log map is defined up to a certain point, which is covering almost all the manifold. It's not anymore the case in this affine setting. We don't have the metric to measure things, but we still have straight lines. And what can we do with that? Well, it turns out that on groups there is a particular connection which is left and right invariant, and it's called the Cartan connection. And if we take the geodesics, you recognize here this is the matrix exponential. On the matrix Lie group, this would be the geodesics that we find for this affine metric, for the Cartan connection. So if we go to the diffeomorphism, well, we find that the geodesics, starting from identity, are the flow of stationary velocity fields. So if you remember what I said at the end of the presentation on demons yesterday, the log demons is exactly that. It's the idea that we can parameterize deformation by the flow of a stationary velocity field. Now, if we just compose on the left or on the right, we obtain geodesic for this Cartan connection. So this is actually the setting which is behind all the log demons and the stationary velocity field. So from a statistical point of view, what can we do? Well, we can't do anymore the Fréchet mean. The Fréchet mean was the minimizing the expected square distance. We don't have a distance. But one of the characterization of the Fréchet mean was the exponential barycenter. When we developed at the mean point, the sum is 0, right? We can take that as an implicit definition. That is called an exponential barycenter. And that is still working, at least locally, in Lie groups. And we can show that the same type of gradient descent algorithm that we used before for computing the mean, it also works in Lie groups. And what we obtain is a mean which is now left and right invariant, meaning that if I'm computing the mean of a set of elements, or the mean of the inverse, that will be inverse of each other. So now I have full compatibility. So to investigate, so I'm going to summarize that. So in matrix group, in theory, we have only the local existence. But if we work out some of the matrix group, it turns out that we have the existence of or the uniqueness of the mean these are more or less the same condition as for Riemannian. So it seems that we do not lose anything by going to this framework. So there's still some mathematical work to do here, but it seems that we do not lose much. Now for the covariance matrix, we can still define that in the tangent space. Now the main problem is that the covariance matrix has no metric. So we can't do anything like PCA. And that is a message that I find interesting to give to you. If you're doing a PCA, this is highly dependent on the metric you use. Even if you take a Euclidean space, you have a huge ellipsoid like that, and you change your basis vectors. Okay? Instead of having a vector which is like that, you take one which is much smaller. And then your two eigenvectors are the eigenvalues are the same. So changing the metric will change your eigenvectors and your eigenvalues. So be very careful about which metric you choose. So in an affine space, we don't have metric, so we can't do PCA, but we can do PGA, and we can do independent component analysis. This is still existing. So it's just to say that this affine setting is quite interesting to work with. So let's go very quickly in the last minutes to application to Alzheimer's disease. So I've already shown how to, yesterday, how the log demons are working. So you should know more or less what it is. We're just parameterizing the deformation by the flow of stationary velocity fields and optimizing this stationary velocity field that best match the two images. And what we want is to use that for describing the changes in the Alzheimer's disease. And what you can see is 2 years apart, there is a big extension of the ventricles. There is a huge decrease of volume of the hippocampus here, and there is a diffuse cortical thinning. And if we're computing the deformation that match these two images, we find this stationary velocity field, and by taking the flow of this stationary velocity field, then we can deform this image so that it matches the other one. So that is the result of the log-Demons algorithm. Now the big question is, if we have a trajectory here, we can fit a straight line here in our space of stationary velocity field, say that this is linear interpolation of the motion. So we would have a vector that is describing this trajectory, a vector describing this trajectory, and we need to set up a parallel transport to be able to transport this vector from one point to another. So just imagine that you have a starting direction in the sphere in Paris. Let's say you have a direction in Paris and you want to transfer it to New York. Okay? So depending on the path you will take, you will transport your vector differently. And depending, you need to define that. And in order to compute that, then we set up, well, two methods, which are called the, Paul ladder and Shields ladder. So I won't really explain what it is, but we can do it in the stationary velocity field. And the global method that we end up with is the following. If we have a single subject and two time points, then we have the log-Demons. If we have more time points, then we can fit a regression, or do a regression, linear regression. So it's basically fitting the geodesic in our affine space of deformation that best explain all the deformation. Now we have a parallel transport method to bring all these trajectories in the template space. And now we can do the group-wise analysis. And what's interesting is that if we just compute what is the mean deformation, this is what we can see on, on 70 Alzheimer subjects. And the mean was evaluated with a time difference between the image of 1 year. And now we're extrapolating to -7 to +7. And if you experimented a little bit with the eigenmodes, usually when you're going to ±3 sigma, it's really the limit. When you're going out, it's just exploding. Okay? Here we're going ±7 sigma, something like that, which is enormous. It should explode. And the fact that it does not explode, and it's still, I mean, if you show that to a neurologist, he will say, okay, that's a young brain, and that's an Alzheimer brain in the end, almost to die. It's nothing like a real brain. It's just computed from statistics. So the simple result, I'm not saying that it is validating anything about the model itself. I'm just saying that the mathematics behind, they're probably not so wrong because it does not explode. That's it. Okay? So I'm just trying to convince you that if we use the right tool, taking into account the curvature and the fact that this is nonlinear, we may have things which are more stable when we're going far away from small variations. If you have small variations, I have nothing to say. I repeat, if you're smaller than the curvature, everything linear will work. If we are larger, then it might be worth going to all this stuff to do nonlinear analysis. So we can do one step further and see what are the longitudinal changes in Alzheimer people versus control. And this is the map that we're finding for the differences, which is all the places where something's happening. So a contraction, all the places in red will be contraction. Places in blue and green are contraction, expansion in green, and contraction in red. So this is more or less known. We're just describing what has been already shown in many, many data. Now what's more interesting is what's happening if we take still the ADNI data set, but just the normal population. So we take 98 subjects in the control population, and we just stratify them according to another marker, which is called amyloid beta. So it's basically, you know that the beta amyloid is one important component in the brain, and it is cut into pieces by some process which is unknown, and by measuring the number of these pieces, or the level, the proportion of these pieces in the CSF, we know that these people who have a high number, they're at risk or not. And so basically with A beta positive, people will be at risk for Alzheimer later. We know that, but we don't know what will happen biologically. So here we just took normal control, A beta positive, so at risk, versus A beta negative, not at risk. Not at risk doesn't mean that they won't have it, just that they are not belonging to the same population. And now we take the evolution over 3 years, so it's not very visible, but we have the velocity field showing what is the average stationary velocity field for the normal evolution. So normal for us will be A beta negative. And the question is, can we see a difference between normal and normal? Or, sorry, control A beta negative and control A beta positive? And the answer is, well, can you see it? That's the evolution for A beta negative, extrapolated over 15 years, so that we can see something, because over 3 years you don't see anything. That's a normal evolution, you almost see nothing. Can you see something? You're good, because I can't. I mean, if I don't zoom, I can't see something. But actually, after 15 years, you might see that actually the ventricles are enlarging a bit faster. The horn of the ventricle here is enlarging faster. So just imagine, we do the measurement on 3 years, we have to multiply by 5 to see something, to barely see something. Now, is this difference, is it statistically significant? The answer is yes. We have significance around the ventricles at least. So it's probably, if we had a larger population, it will probably be significant at other places. But the nice thing is that if we just compute on the stationary velocity field trajectories, so it's a multivariate test, we have statistical significance. If we take the Jacobian value, so the change of volume, as usually we do, there is no significance. And the reason is the Jacobian value is a derivative. It's a Jacobian. I mean, you're just computing differences. And when you have a bit of noise, computing differences is just enhancing noise. Okay? And more noise means less statistical power. So the explanation is just that. I mean, by reducing and keeping to velocity fields instead of their derivative, we can see things that we can't because they are more stable. And if we just look at what's the difference, this is the progression. So in red, it's the places where there is something happening, so atrophy, for the normal A beta negative. This is what we need to add to this progression for the A beta positive. And this is what we would need to add for Alzheimer's disease. So you see that the pattern that we have here resembles quite a lot this one, but it's 10 to 15 years before. It's way before the Alzheimer's disease is diagnosed or even suspected. So it means that this is something which might be quite interesting for early drug development, and we are now trying to apply that on retrospective data on some pharmaceutical company to try to see if actually we see something in some of the studies where they found nothing. And that might be a useful tool for clinical study. So just to finish, this group-wise analysis, which is discovery, we can also turn it into some kind of measurement. And the idea is we can try to see what are the regions in which there is something happening. And if we define several regions, so these ones are defined automatically from the velocity fields over the whole population, we can turn that into subject-specific with Atlas II subject registration. And now on these regions, we can measure what's the flux of the stationary velocity field. So this means what is the loss of matter in specific regions. And just by using that, that was at the challenge 2 years ago at MICAI, we just applied the method and gave the result to the statisticians who did the ranking with other methods. So almost all the other methods were segmenting the hippocampus. Here we have a fuzzy segmentation. You see the region is very they are quite fuzzy. We just transport them with intersubject deformation to a subject and measure the average flux weighted by that. And we were ranked actually first I think it's first on the right hippocampus and second on the left hippocampus in the efficiency, the statistical efficiency of the method. So I'm not saying that this is going to revolution the world. I'm just saying that this is another experiment that showed that the method is actually sufficiently robust to be able to compete with methods, segmentation methods, where people are working on for the last 10 years. Okay, so I think I'm gonna finish by just advertising for the stationary velocity field framework. In this framework, we can also design other types of statistical analysis, and one of them is to have parametric deformations, and the idea is just to have locally affine deformations and recombine them with different weights into a single stationary velocity field, and when we take the exponential, we obtain a smooth map. And this is an example of here a tracking of the motion in the heart with only 17 regions. So it means 17 times 12 parameter, 200 parameters. So this is a diffeomorphism which is parameterized by 200 parameters. And now we can even try to analyze, decompose the deformation into time, independent time and space. And in that case, by using, so it's not anymore PCA, it's tensor decomposition, but by using 8 temporal modes and 3 spatial modes, we have 24 parameters that basically characterize here the motion. And we can show that, I mean, the first temporal mode is basically the volume curve, and the second one are derivative of that. And for the spatial modes, we have very, very different setups, well, very different modes that are appearing for healthy versus tetralogy of Fallot. So it's just to say that this is, I mean, this is one very simple way to linearize deformations, the stationary velocity fields. So I'm going to skip that one just to go to the conclusion. So what I try to explain you in this talk is what are the structures that we can use for doing statistics on nonlinear shapes. And in physics, if you take the history of physics, that was first a flat space, and then came Einstein with the curvature of the space. And basically, there's one key notion in the development of the relativity, which is that the law of physics should be the same at every point of the universe. And that is this requirement that is leading to some kind of homogeneous, so here it's a pseudo-Riemannian metric, on the manifold, on the space-time manifold. So one of the key questions that we can have, after that, once we have the big structure of the space, we can try to look at what's the fine structure of the matter in the space, so the filaments and things like that. So for anatomical shapes, I can have the same question. Is there a global structure which is very simple, kind of homogeneous, where we could compare things at a global scale? So that's basically for the Earth, it would be, well, the spherical shape. Now, if we want to go to finer details, once we have the spherical shape, we can try to see that, well, it's a bit, not exactly a sphere at the poles, it's more an ellipsoid, and then we can try to draw the mountains. So we can try to see very fine details. But if we don't have the right global structure, then there's no way we can do something else than a local analysis. So here's the question that I'm asking, or I'm trying to answer. What's the right geometric structure to do these statistics? And this is just an advertisement. Every 2 years or so, we have a workshop at MICAI to try to discuss this kind of stuff. So if you want to try to follow what are the discussions on that, that is the right place to do, well, deep mathematics. And MICAI just next to it is the right place to try to apply it. And I hope we can continue to talk together to better describe this type of statistics and use them for applications.